One thing that you can do with vectors is you can actually magnify them. And this isn't something that's all that surprising. If a vector represents the amount of force being applied to an object, then you can imagine that, well, you can increase that force. If you're pushing against an object and you're just kind of rolling along, you decide to push twice as hard, well, you've literally pushed it twice as hard. You've doubled the amount of force involved. And we're going to find that that translates very directly with scalar multiplying. In this case, the word scalar, by the way, if you're not familiar with this, the word scalar is really just referring to a numeric quantity. There's a couple different ways you can define this, but I really think just numeric, and I tend to think magnitude. This is the part that's probably more important, is this. A scalar value is some kind of numerical magnitude. So if I say I'm pushing on something twice as hard as I was, that numeric value, that magnitude of the scalar value, would just be 2. And so for the example we see here, it says to find 4 times your original vector v. You're going to find that this is really similar to sort of like a distributive property or something like that. If I'm pushing on an object, let's say I'm pushing on something right here. Let's say this is how I'm pushing in the original. If I want to double that magnitude, I'm going to do that again, basically. So I would say to get this whole resultant here, I'd need to push twice as hard. Well, notice that what would happen is I would get 2 copies of that horizontal component. I would also get 2 copies of the vertical component combined together to make this total vertical component here. So if I doubled the vector, I doubled its horizontal and doubled its vertical components. So for this problem, they're saying multiply by 4. They want a vector 4 times as large. Well, all that tells me to do is take my original vector and multiply it by 4. In fact, I can write it this way if I'd like and say kind of 4 times this vector. And it's just a simple matter of saying 4 times negative 2, which is negative 8. And then let's see, 4 times 19, well, that's 40, and 36, that would be 76. It's a pretty large y component, but that's okay. This is our 4 times v. Now, it's important to point out that because we are simply magnifying our value, we're making it more powerful, but we're not changing its direction. So this vector here that I've created would actually result in the exact same theta value, our same angle of measure from, say, the positive x-axis. So over here, for example, it should be clear from the way I've drawn this triangle, this angle down here in the bottom left corner didn't change when I extended this triangle, when I created this similar triangle to show the magnified version of my vector. So we see with scalar multiples, they're really a one-dimensional conversation. They only affect the magnitude. They do not affect direction. If something's affecting the direction, you're probably dealing with another force being put into play. So maybe I'm pushing something along and somebody else runs up and hits it from the side. Now the direction is going to change, but that's because I've applied that other force. So if you see a problem where they ask you to multiply by a number and you have a vector to work with, all you have to do is multiply the components by that number to get your resultant vector. If they want to know a different form, if you wanted to go in and find the magnitude and the direction of this thing, keep in mind that for magnitude, you could just do the Pythagorean theorem. So just out of curiosity, we could just go ahead and find that. And then to find direction, well, we've seen in previous videos that to find your angle measured from the positive x-axis counterclockwise, you can take tangent inverse of your y component divided by your x component. And I want to point out something with this because this is another way to illustrate and demonstrate that your direction will be the same. And first of all, I'm going to go to mode on my calculator. This is always a good thing to do, especially if it's been reset. Make sure we're switched over to degree mode. I want to notice that 76 divided by negative 8 is actually the same thing as 19 divided by that negative 2. The ratio of y to x is the same for both of these guys, which means I'll get the same inverse tangent statement down here either way. This is kind of just further evidence that scalar multiples like this do not change direction. So kind of pointing that out, but I should probably also go ahead and find that direction angle. And now I'm seeing something here that I'm not really happy with. I'm seeing negative 84 degrees. And so I'm going to put a little question mark because it's not really what we want to deal with. Negative angles are measured in a clockwise fashion. So that means that instead of moving this way like we want, it's moving this way. So we don't want that. We want to go back to our vector here. We have a negative x component and a positive y component. That should be something out here, not something down here. So let's just add 180 degrees to that. In fact, I can do that right here in the calculator. And we get about 96 degrees. So adding 180 here will give us the proper angle that we want. In fact, this is not much bigger than a right angle, which is kind of interesting. But we would see here that we'd have a 96 degree angle, and just for the sake of thoroughness, I skipped over our Pythagorean theorem. Let's go ahead and jot that down. We're seeing about, now this one's going to be a little weird to some people, about 76.4 for our magnitude. And you might look at that and go, well, hold up. That's basically one of our side lengths. And you're not wrong. It seems to me that the vector we have to work with here is something very steep, like this, that is moving to the left only a little bit. It's only going 8 to the left, but it's moving up a lot, which means this resultant and this vertical component are not going to be that different in magnitude. So this is just kind of a overall spiel here of kind of what you could do with this, where you could go. For this problem, this right here was the actual answer. It did not specify, it didn't say to change it to magnitude and direction. But this vector would also be written in direct notation as 76.4 magnitude with an angle of 96 degrees. So this is an alternative answer that you could have had here, depending on what they asked you to do.